Hi everyone. In this video, we are going to discuss about how to find out the highest power of a prime number in n factorial. So here we are going to use the concept of factorial. First, we need to understand what a factorial is. Well, factorial of an integer is equal to 1 times 2 times 3 times 4 times 5 all the way up to that integer, right? So it's the continued product of all the integers between 1 and that number. For example, if we take a number 15, and what would be the factorial of 15? Well, factorial of 15 is going to look like this. So let me write it down like this. 15 factorial. 15 factorial would be the product of 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8 times 9 times 10 times 11 times 12 times 13 times 14 and times 15. So this product, whatever is the result of this product will be equal to factorial 15. 15 factorial, factorial of 15. So factorial is a function that indicates that it is a continued product of all the integers between 1 and that number. And obviously we cannot take factorial of fraction, we need to take factorial of positive integers. And also 0 factorial is also possible. 0 factorial is actually equal to 1. So any non-negative integer can have a factorial value. So in this example, let's play with the factorial 15 and say, for example, we want to find out the highest power of 2 as a prime number. So we are going to take 2 as an example. In fact, we could have done it for 3 or 5 or 7, but for demonstration, let's go with the prime number 2. So from this factorial, we are going to try and find out what is the highest power of 2 in this particular value. It's a big number. Obviously, it's going to be a really big number. And we want to find out what is the power of 2 in this number. You know, if we have to do prime factorization, then what will be the power of 2 in this big number? Well, we can clearly see that we have one of the 2's right here. So this will be one of the 2's. Then here are 2 more 2's. Then again, here is one more 2 right here. Then again, 3 more 2's right here. One more 2 right here, then 2 more 2's right there, and then one more 2 right there. So we can sum up all of those to find the highest power of this prime number 2 in the 15 factorial, right? Now, because it's 15, we can easily, write it like this on a piece of paper and find out, okay, what would be the highest power of 2. But if you are given a really large number, say for example, factorial of 100 or maybe factorial of 1000 or factorial of 5000, and you have been asked to find out what would be the highest power of the prime number 2 in that factorial, it will be very difficult to figure it out by writing it on a piece of paper like this and then, somehow finding out what are the factors of 2 we have. So we have to come up with some sort of a process to find out what will be the highest power of a prime number in a certain factorial. And actually there is a formula. I have written that at the top of the screen right here. You can see that it would be the greatest integer of n divided by p plus greatest integer of n divided by p squared plus greatest integer of n divided by p cubed, and so on until this greatest integer value becomes 0. So we need to use this formula to find out what is the highest power of this prime number p in n factorial. Now the question is, where did this formula even come from? And that's what we are going to prove in this video. So now let's start our game. We have 15 factorial, so we are going to take n as 15. So here we are assuming that 15 is actually our n factorial. Our n factorial is actually 15 factorial. So we are taking n as 15 just for demonstration, and then we are going to find out the highest power of 2 as a prime number. So in this case, we are taking 2 as our p. So 2 is the p and n is 15. So 15 is the n and 2 is the p. With that assumption, we are going to try and prove this particular formula, right? So let's get started then. Now, before we go too far, one other important aspect we have to understand is, say suppose between 1 and 15, how many multiples of 2's are there? Meaning how many even numbers are there? Or I should not say even number, I should say how many multiples of 2's are there? Now here you see I have already underlined, so it is 1, 2, 3, 4, 5, 6 and 7. So looks like there are 7 multiples of 2's between 1 and 15. Now where is that 7 number coming from? Well, if you think about it, if we divide 15 by that prime number, that will give us how many multiples of that prime number exist between 1 and 15, right? So now this is what I'm going to do, that if I divide our number 15, say 15 and I'm going to divide that by 2, and this is going to give us the answer 7. This is actually 7.5. However, if we take the greatest integer of this, we are going to find that this is actually 7. And you can see the pink underline that I have right here, that there are 7 of them. There are 7 multiples of 2 exist in this 15 factorial, right? You can see that there are 7 multiples of 2, right? So this is one thing that we have to keep in mind as we progress through the proof. We will be using this particular concept as many times as we need to figure out how many multiples of 2 would be there. Now also you should imagine this as n divided by p. That's the first one, n divided by p, and the greatest integer of that. That's going to tell us how many multiples of 2's we have in the first round, meaning in this original picture. So this is actually equivalent to n divided by p, greatest integer of that, right? So now let's get started. And as you can see, so in here what we have, I'm going to start writing from here. So let's first write down all those multiples of 2's, and let's write the other terms separately, right? So first I'm going to use a parenthesis and I'm going to group all the multiples of 2's together. So I'm going to write 2 times 4 times 6 times 8 times 10 times 12 times 14, right? So I'm going to group them together because I'm interested about those factors only, because that is where I have the prime number 2. In all other factors, the 2 does not really exist. If you think about 1 or 3 or 5 or 7 or 9, they really do not have a factor of 2. They really don't have 2 inside them. So I'm not interested about them. So what I'm going to do, I am going to write all the multiples of 2's like this, and then times whatever is remaining. Well, what is remaining? We have 1, then we have 3, then we have 5, we have 7, we have 9, we have 11, we have 13, and also we have 15. So this is our factorial 15. I just rearranged a little bit and I'm writing it like this. Right? Now from here you see that, can we write it like this? Can we write it as, I'm going to write it as, now how many multiples of 2's we have here? We have 1, 2, 3, 4, 5, 6, 7. So if you take 2 out from each of these factors, so if you take 2 from each of these factors, then how many 2's we'll get? We'll get 2 to the power 7. We'll get 7 of them, and everything is in multiplication form, right? So from the first factor I get a 2, from the second factor I get a 2, from the third factor I get a 2. In the first round I'm going to take only the 2's out. If you are thinking that, hey, in the second factor here we also have couple of 2's, but I'm going to take only 1, 2 out of each of these factors in the first round. So we have 7 of them here, 2, 4, 6, 8, 10, 12 and 14. That's 7 multiples of 2's, and I'm going to take the 2 out of each of the 7 factors there. So I'm going to get 2 to the power 7. That's 7 of the 2's I get, and then within parenthesis what is left? Well, from the first factor we will have 1, from the second factor we will have 2, from the third factor we will have 3, then from the fourth one we will have 4, then from the fifth one we will have 5, then from the sixth one we will have 6, and from the seventh one we will have 7. And then outside whatever we have, this number right here, I really don't care about this portion right here. This is just an integer. It is some integer, and I am really not interested about that integer because it does not contain a factor 2. So I am really not interested, right? So what I'm going to do, I'm going to write it as some integer a. Let me just say like a lowercase a, right? So that's just some integer a, and I'm not really interested about that because I'm interested about only the factors that contains 2, but those other factors don't contain 2. So I'm just simply replacing them with some integer a, right? So now from here you see, okay, so we have 2 to the power 7 times this, right? Now you think about these remaining factors within the parenthesis. Now how many factors we have? Well, we have 1, 2, 3, 4, 5, 6, 7, and out of those, how many multiples of 2's we have? We have 1, 2 and 3. We have 3 of them. And how did I get this number 3? Well, this 3 is actually, if you think about it, this is nothing but 7. So if you say 7 divided by 2 and you take the greatest integer of that, that's going to give you 3. So now we know that we clearly have 3 multiples of 2's inside there. Alright, now if that is the case, I'm going to erase this and let me say, okay, so now I'm going to rewrite this thing as 2 to the power 7, and then within parenthesis I'm going to keep only the multiples of 2's, like 2 times 4 times 6. Right, and then I'm going to bring everything else outside. Outside I already had another integer a, and then I'm going to bring this 1, 3, 5 and 7 outside. So 1 times 3 times 5 times 7. So I'm going to bring all of them outside of the parenthesis. And then from within the parenthesis, what I'm going to do, I'm going to again bring out as many 2's as I can. So how many 2's I have? Well, I have 1, 2 and 3. I have total 3 2's there, right? I know that there is one more 2 in the 4, but we'll do that in the next round. So in this round, I'm going to bring out only the 3 2's out of here. So a 2 from the first factor, and then one more 2 from the second factor, and one more 2 from the third factor. So I already had 2 to the power 7, and then now also I'm getting another 2 to the power 3, and then within parenthesis what we are going to be left with? Well, we'll be left with a 1 and a 2 and a 3, and then times we have this a multiplied by a bunch of other integers, and I'm going to call it a b. I'm really not interested about them, so I'm just using symbolic here, right? I'm using like algebraic symbol here to indicate that hey, they are some integer, they are just some integer that I'm not interested about, but we really cannot ignore it, so I'm keeping it, but again it does not do anything for our purpose, right? So I'm just keeping it like that. So now you see, now we are at a place where we can write it like this. So we can say, okay, this is nothing but 2 to the power 7 plus 3. We can add the exponents because everything is in multiplication form, and then from within the parenthesis, again what I'm going to do, I'm going to keep only the multiples of 2's. Now how many multiples of 2's we have? We have actually 1. Now where did I get that value 1? Well, if you think about it, we have total 3 factors, and if you say 3 divided by 2, take the greatest integer of that, what are you going to get? We are going to get 1. That means between 1 and 3 we have only one multiple of 2. Right? So if we keep only the multiple of 2 within the parenthesis, then it is going to look like this, and then we already have the b right here, and then I'm going to bring the 1 and the 3 outside, so I can say times 1 times 3, and we are going to write it like this. So now we are going to say, okay, it is now going to be 2 to the power 7 plus 3, and then from within the parenthesis, you see I can bring out one more 2, right? Because there is only one factor of 2, and I can bring out one more 2. So let me say, okay, this times 2, and then within the parenthesis we are going to be left with a 1, and then times b times 1 times 3. Let's say this is nothing, this is like a c. So from here you can say, okay, so this is looking like 2 to the power 7 plus 3 plus 1, because we have this one other factor, right? So I'm adding the exponents there. So 2 to the power 7 plus 3 plus 1, and then times we have 1 times c, so we can write it as c. So finally you see that we have been able to find out what is the power of our prime number. So the power of our prime number in factorial 15 is actually this sum right here. This is what we are interested about. The 7 plus 3 plus 1, that is what we are interested about, that there are actually 11 2's hiding in factorial 15. That means the highest power of 2 in factorial 15 is going to be 7 plus 3 plus 1, which is equal to 11. Now if we try that in the formula that we had, if we try it in our formula there, so the formula that we had the formula like this: n divided by p, greatest integer, plus again n divided by p squared, greatest integer, plus n divided by p cubed, greatest integer, and so on. So here if we use 15 in place of n, so what we get? Well, it will be greatest integer of 15 divided by 2. 2 is our prime number in this example, so it will be like this. Then it will be 15 divided by 2 squared, which is 4. 2 squared, that is p squared, which is 2 squared, and then again 15 divided by 2 cubed, that is 8. And then do we need to continue anymore? No. Why? Because then the next item would be 15 divided by t to the power 4, which is 2 to the power 4, that would be 16. And guess what? This greatest integer will come out to be 0. This one will become 0. So we really don't need to continue anymore. So we can pretty much stay with the 3 terms here. And now let's see what we get. So from here we are going to get 15 divided by 2, that is 7.5, greatest integer would be 7, plus 15 divided by 4, that would be 3 point something, greatest integer would be 3, plus 15 divided by 8, that would be 1 point something, so the greatest integer will be 1. So this is equal to 11, and that is the highest power of our prime number 2 in factorial 15. Now so far we have been able to validate that yes, the formula is actually working based on what we noticed, right? Now I am going to show you where the formula even came from? Actually, the formula came from this derivation only. So if you look at this derivation, we should be able to figure out how many 2's we are getting. Now here you see the 2 to the power 7 that we have right here. The 2 to the power 7 is nothing but the number of multiple of 2's between 1 and 15, right? So that is that 7 right here. We can say, okay, this 7 is nothing but n divided by p, the greatest integer function of that is actually the 7. So in our case, the 7 that we got right here, 2 to the power 7, that is nothing but n divided by p. It's just how many multiples of 2's we had between 1 and 15, right? That is that 7. And then the other 3 that we got, well, if you think about it, so once we are done with that, how many terms did we have here? In here, if you look at this particular portion right here, now I'm going to use a different color. I'm going to use the white color. If you look at this portion right here, how many terms we have? Well, we have n divided by p, greatest integer of n divided by p. We have so many terms here. Now from there again, so if we have so many terms in there, in this case, it is actually 7 terms there, but we can use the symbol x and we can say, okay, we have actually greatest integer of n divided by p, so many terms we have there. Now in that many terms, how many multiples of 2's we have? Well, the number of multiple of 2 would be again whatever that is, the n divided by p, and then I have to divide that by p again, because we are trying to find out how many terms we are going to get in this other parenthesis right here. How many multiples of 2's we are going to get? Well, we are going to get so many multiple of 2's like this, the greatest integer function of this, and this is actually nothing but n divided by p squared. If you carefully look at it, this is nothing but greatest integer of n divided by p squared. So this is saying that, hey, in the second round, you are going to get only so many multiples of 2's. In the first round, you had these many multiples of 2's, and then in the second round, you get so many multiples of 2's. Alright, very good. Now in the third round, how many multiples of 2's we get? Well, I'm again underlining with a white color line here. So you can see that in the third round, we're going to get how many multiples of 2's? Well, the formula would be again how many ever we had before. So before we had n divided by p squared, we had so many, and again I have to divide that by p to figure out how many multiples of 2's that we are going to get. And this is actually nothing but n divided by p cubed, and greatest integer function of that, right? So in the third round, how many multiples of 2's we are going to get? Well, that's actually n divided by p cubed, because we had n divided by p squared number of terms, and then we divide that by 2, which is p in this case, and we are going to get so many multiples of 2's. And that is why finally we get that one of the 2's right here, which is right here. I'm going to do a white circle right here. You see that one of the 2's that we got right here, that's actually n divided by p cubed, and the greatest integer of that. So every time you have to understand this, that in at the very beginning, how many multiples of 2's we had? We had greatest integer of n divided by p, so many multiples of 2's we had. Then in the second round, how many multiples of 2's we had? We had n divided by p divided by p again, because we had only so many multiples of 2's, and then from so many factors again, how many multiples of 2's we get? We get n divided by p squared, so many multiples of 2's. Now again, once we take out a 2 from each of those factors, then again we are going to be left with n divided by p squared number of terms, and again there how many multiples of 2's we have? We have n divided by p cubed number of multiples of 2's that we have in there. So this is how this iteration will go on until we are done capturing all the factors of our prime number. So from here, ultimately, you see that our 2 to the power 7 plus 3 plus 1, this is actually, so now I'm going to write this 2 to the power 7 plus 3 plus 1, that is actually like this. So you can say, okay, this is our prime number, and then the 7 is actually 15 divided by 2, greatest integer of that is the 7, and then the 3 that we have, that is actually 15 divided by 2 squared, which is 4. I'm going to write it as 2 squared, greatest integer of that. And then the 3 that we have, that is again, it is actually 15 divided by 2 cubed, which is 8, but I'm going to write it as 2 cubed, 15 divided by 2 cubed, and the greatest integer of that. So that is the power of our prime number 2 that we got from factorial 15. So you can see that how in the first round we got 15 divided by 2, so many multiples of 2's. Then in the second round we got 15 divided by 2 squared, so many multiples of 2's. Then in the third round we got 15 divided by 2 cubed, so many multiples of 2's. Then if we had even more 2's, like a fourth round, yes, we could have continued on to the fourth round if our number was bigger than 15 factorial. And it really doesn't matter how large the number is, meaning how large that n is. You can pretty much use this particular formula and you can see how the formula is developing, because in the first round, again I repeat, in the first round we had n divided by p, so many number of multiples of 2's. Then in the second round we had n divided by p squared number of multiples of 2's, and in the third round we had n divided by p cubed number of multiples of 2's, and that is how we are gathering the number of 2's that we have in this large number, which is the factorial 15, right? So now if we replace all of this with n and p, so this particular value right here, let me show you with a pink box right here. So this is the power of our prime number. This is the power of our prime number in factorial 15. So this power, this is the item that we are interested about. So this is actually nothing but it is actually n divided by p, that is the first item, of course greatest integer of that, plus n divided by p squared, greatest integer of that, plus greatest integer of n divided by p cubed. So in our example we stopped at p cubed because we only went with number 15 and prime as 2, but it could continue even further until this greatest integer start to become 0, right? So that is where the formula came from, and this is the formula that says that in factorial n you will have so many p's, where p is a prime number, right? In this factorial n, this is the number of p's, meaning the power of the prime number p. So this is actually the power of the prime number. So let me write it down here. This is the power of, or the highest power, you can say, power of prime number p in n factorial. So you can say in where? In n factorial. In n factorial. So this is nothing but the power of the prime number p in n factorial. So this is the power of the prime number p in n factorial. Now let's take an example. So suppose you are given that, hey, can you find out what is the highest power of 3 in factorial 50? Sure, we can do that. So we are talking about n as 50 and we are talking about prime number as 3. So we have been asked to find out the highest power of 3 in 50 factorial. So here n factorial is 50 factorial and our prime number is 3. So we are going to do the same logic here. So we'll say, okay, the highest power of 3, or we can say power of 3 in 50 factorial, power of 3 in 50 factorial is equal to the greatest integer of the first one would be 50 divided by 3, and then we'll do 50 divided by 3 squared, greatest integer of 50 divided by 3 squared, and then we'll do again 50 divided by 3 cubed, and then again greatest integer of 50 divided by 3 to the power 4. And do we need to continue anymore? Probably not, because 3 to the power 4 would be 81, right? So I think this one is already not necessary. This particular one is not necessary even. But let's see. So here we can say, okay, 50 divided by 3, that is actually 16. The greatest integer would be 16. It would be 16 point something. So we'll take 16. And then 50 divided by 9, which is 3 squared. 50 divided by 3 squared, that means 50 divided by 9. That would be 5 point something. So you will take 5 plus 50 divided by 27, which is 3 cubed. That would be how many? That would be just 1. Okay. And then 50 divided by 81, well, that is actually 0. So we really don't need to continue anymore. We can stop right there. So from here we get, okay, the highest power of 3 in 50 factorial would be 16 plus 5 plus 1, that is 22. So we have so many 3's hiding there in factorial 50. I hope everything made sense so far. Thank you for watching. See you in the next video.